This factory is producing a large slewing bearing, a heavy-duty bearing that allows massive structures to rotate smoothly while carrying both vertical and side loads. The process begins with thick alloy steel billets. Each piece is measured and cut to the required size before entering the forging line. The steel blocks are loaded into a high-temperature furnace and heated until they reach roughly 200 degrees Celsius. At this temperature, the steel becomes soft enough to reshape without cracking. Uniform heating is critical. If the center remains too cold while the outside becomes too hot, the metal may deform unevenly during forging and create internal stresses that affect the finished bearing. The glowing billet is transferred to a massive hydraulic forging press. Repeated blows compress and reshape the steel, gradually transforming the rectangular block into a thick round blank. Forging does more than change the shape. The intense pressure refines the internal grain structure of the steel, helping produce the toughness needed for a bearing that may carry hundreds of tons in service. Workers and heavy manipulators continually rotate the hot part, so the deformation remains even around the entire circumference. Once the basic disc has been formed, the center is opened, and the hot steel is worked into a ring. A large mandrel and forming tools enlarge the opening while maintaining the required wall thickness. Creating the ring directly from forged steel gives the bearing a continuous structure without welded joints in the main load-carrying section. That becomes especially important when the finished bearing is exposed to repeated shock, rotation, and heavy loading. After forging and cooling, the rough rings are moved to the machining department. The crane positions one of the heavy blanks onto a large vertical lathe. At this stage, the surface is still covered with forging scale, and the dimensions are intentionally oversized. The lathe removes this excess material and creates the accurate faces, diameters, and shoulders needed for the bearing assembly. The next machines produce the external gear teeth around one of the rings. A gear cutting tool removes metal tooth by tooth as the ring indexes through the machine. These teeth allow an electric or hydraulic drive to rotate the entire structure mounted above the bearing. Tooth spacing and profile have to remain consistent because poor gear geometry can cause noise, uneven loading, and accelerated wear. Steel balls and polymer spacers are now inserted between the two bearing rings. The balls carry the load while allowing the rings to rotate with relatively low friction. Spacers keep neighboring balls separated, reducing direct contact and helping distribute lubricant around the raceway. Workers add the components one by one through an access opening until the entire circular track is filled. Finally, the bearing is packed with grease, sealed, and carefully inspected. Lubrication separates the steel surfaces, reducing friction and wear, while also helping protect the raceway against corrosion. What began as a solid block of hot steel has become a precision slewing bearing capable of supporting enormous machinery while allowing thousands of pounds or even tons to rotate smoothly and reliably. A tunnel boring machine may weigh thousands of tons, but its ability to break through hard rock depends on much smaller components like this heavy-duty roller cutter. Production begins with a solid, high-strength steel blank mounted in a large CNC lathe. Cutting tools remove the rough outer surface and gradually form the tapered cutter body. The partially machined body moves through additional CNC operations. Coolant floods the cutting area, while rows of precisely positioned holes are machined around the outside surface. These openings will hold the hard-cutting inserts that actually contact the rock. Their spacing is carefully engineered so the load is distributed around the cutter rather than concentrated in only a few points. Accurate machining also ensures every insert sits at the correct depth and angle. Now the carbide cutting buttons are pressed into the machined holes. A hydraulic press applies controlled force to seat each insert tightly inside the steel body. These buttons are commonly made from tungsten-carbide, a material far harder and more wear-resistant than ordinary steel. During tunneling, the cutter repeatedly rolls against abrasive rock under extreme pressure, so the carbide takes most of the direct wear, while the tougher steel body absorbs the larger mechanical loads. With the inserts installed, the cutter returns to machining equipment for final finishing. The body is rotated while workers check the surface and remove remaining material around the mounting areas. Metal chips are cleared away and the internal bore receives particular attention. The outside may do the cutting, but bearing alignment inside the tool is just as important. Poor geometry here would create uneven rotation, heat, and premature wear. The central shaft and bearing components are prepared separately. Multiple rows of cylindrical rollers are carefully assembled around the polished bearing surfaces. These rollers allow the cutter body to rotate under extremely high radial loads with relatively low friction. Workers install them one by one and check their seating by hand. At this scale, a missing, damaged, or incorrectly positioned roller could affect the entire load path through the cutter. The finished shaft assembly is lowered into the carbide-covered cutter body. Workers guide the components together carefully to avoid damaging the polished bearing surfaces. Once assembled, lubricant is introduced through the service port. Grease creates a protective film between the moving metal surfaces, reducing friction and helping keep abrasive dust and moisture away from the bearings during underground operation. The completed cutter is mounted in a fixture and rotated by hand. Technicians check for smooth movement, excessive resistance, and abnormal play in the bearing system. This simple test can reveal assembly problems immediately. A cutter that does not rotate freely would drag instead of rolling across the rock, generating unnecessary heat and rapidly destroying both the carbide inserts and the bearings. Finally, the completed cutter is protected and packed for shipment. From a solid steel blank to precision machining, carbide insertion, bearing assembly, lubrication, and inspection, this compact component is built to survive the brutal forces required to help a tunnel boring machine cut its way through solid rock. A good handsaw has to do two things at once: remain flexible enough to survive repeated bending, yet keep hundreds of tiny cutting teeth sharp enough to slice cleanly through wood. This craftsman begins with a coil of thin, high-carbon saw steel. A section is cut from the coil, straightened on the workbench, and checked against the required blade dimensions. The flat steel blank now moves to a mechanical tooth-cutting machine. The craftsman feeds the blade steadily while the punch repeatedly removes small sections along one edge, creating the saw's distinctive row of teeth. Each tooth has to remain similar in height, pitch, and spacing. These dimensions determine how aggressively the saw cuts and how smoothly it clears wood chips from the kerf. Instead of grinding every tooth individually from solid steel, mechanical punching creates the basic geometry quickly and consistently, while still leaving room for hand finishing later. Once the tooth pattern is complete, the craftsman begins one of the most important manual operations: setting the teeth. Using a small hammer and specialized support tools, alternating teeth are bent slightly to opposite sides of the blade. This creates a cut, or kerf, that is slightly wider than the steel body itself. Without this offset, the blade would rub against both sides of the wood and quickly bind inside the cut. The amount of set must remain controlled. Too much makes the saw rough and inefficient, while too little increases friction. The tooth line is inspected closely and adjusted where necessary. A file is passed across individual teeth to refine their shape and cutting edges. This is where experience makes a noticeable difference. The craftsman looks for teeth that sit higher, lower, or at a slightly different angle from the rest. A consistent tooth line allows more teeth to share the cutting load instead of forcing only a few points to do most of the work. Now the metal blade is paired with its wooden handle. The shaped tang slides into a slot at the end of the handle where the fit is checked by hand. A drilling machine creates the holes for the fasteners that will lock the two pieces together. Accurate hole placement matters because the handle has to remain aligned with the blade. If it sits at an angle, the user will naturally twist the saw during each stroke, making a straight cut much harder to maintain. Brand markings and identification labels are applied to the finished saws. The craftsman also gives each completed tool another visual inspection, checking the handle, fasteners, blade alignment, and tooth condition. Despite the simple appearance of the finished product, several operations have already depended on manual judgment rather than automation alone. The finished saw is then packaged for sale. From coiled steel to a working hand tool, this process shows why an experienced craftsman can still make a difference in something as familiar as a saw. These traditional Korean brass cups begin with one of the oldest metalworking methods still used today, sand casting. Workers pack fine foundry sand tightly around the patterns by hand. The sand must be firm enough to hold its shape, but still allow gases to escape when molten metal enters the mold. More sand is added until the molding box is completely filled. Workers repeatedly press and ram the material to eliminate loose areas, then level the surface before turning the mold over. Consistent compaction is important. Sand that is too loose can collapse during pouring, while excessive packing can prevent gases from escaping and leave defects on the casting. Once the surface is prepared, the two mold sections can be separated. The original patterns are carefully removed, leaving hollow cavities shaped like the finished cups. Workers repair the edges by hand and form small channels connecting each cavity to the main pouring point. These runners allow molten alloy to reach several pieces from a single pour. Small vents are also created through the sand. They give hot gases a controlled path out of the mold instead of trapping them against the metal surface. The two halves are aligned and closed tightly together. At the same time, the copper-based alloy is heated in a furnace until it becomes fully molten. Traditional Korean brass and bronzeware depends heavily on alloy control. The proportions of the metals influence hardness, color, sound, and how well the finished piece responds to machining and polishing. When the temperature is right, the crucible is lifted from the furnace. After the alloy has cooled enough to solidify, the sand mold is broken apart. The newly cast pieces emerge, still connected by the metal runners that carry the liquid alloy between cavities. At this stage, the surfaces are rough and dark from heat and sand. The castings are separated, and excess metal around the gates and edges is removed before precision finishing begins. Each rough cup now moves to a lathe and grinding station. The casting is mounted on a rotating fixture, while cutting tools remove the uneven surface and bring the rim, interior, and outside profile closer to their final dimensions. Machining is especially important with sand casting because the mold provides the basic shape, but not the smooth surface expected from finished tableware. The craftsman controls the tool by hand, removing only enough metal to create an even wall and clean edge. Workers smooth the rim, polish the inside and outside, and inspect the surface for remaining scratches or casting defects. What began as molten alloy and packed sand has now become a finished piece of traditional Korean metalware, made with a process that combines centuries-old casting knowledge with careful modern machining and hand finishing. This traditional Korean bronze kettle begins with a process that has changed surprisingly little over generations. The master first prepares a metal pattern that represents the basic shape of the kettle. It is placed inside a molding box and surrounded with specially prepared foundry sand. The pattern is carefully removed, leaving behind a hollow impression of the kettle. The craftsman repairs the edges by hand and smooths areas where loose sand could interfere with the molten metal. A second section of the mold is prepared in the same way, along with the internal core that creates the hollow space inside the vessel. This is where experience becomes important. The wall thickness of the finished kettle depends on maintaining an even gap between the outer mold and the inner core. The mold sections are compacted again and fitted together. Small channels are formed to guide molten bronze into the cavity and allow trapped gases to escape. These passages may look simple, but their position affects how completely the metal fills the kettle. If the bronze cools before reaching every section, the casting can be incomplete. If gas becomes trapped, it may leave internal pores or surface defects. The completed mold is then secured and prepared for pouring. Now the copper-based alloy is heated inside a crucible until it becomes fully molten. The craftsman watches the furnace closely, judging the condition of the metal before removing the crucible. The glowing bronze is poured steadily into the sand mold. Temperature and pouring speed both matter. The metal must remain fluid enough to reach thin sections of the kettle, but excessive turbulence can pull sand and oxidation into the casting. Once the mold is filled, the metal is left to cool and solidify. The sand mold is broken away, revealing the rough bronze kettle for the first time. At this stage, the surface is dark and uneven, with extra metal remaining around the pouring channels. The casting is heated again and then cooled in water. This thermal treatment helps prepare the metal for the machining and finishing operations that follow, while also making it easier to remove scale from the surface. The rough kettle is now mounted on a lathe. As the body rotates, cutting tools remove the casting skin and gradually reveal the clean bronze underneath. The craftsman machines the outside profile first, then works inside the vessel to create a smoother and more uniform wall. This is a critical stage. Removing too little metal leaves an uneven surface, but cutting too deeply can make the kettle unnecessarily thin. Machine accuracy provides the rotation, while the craftsman controls exactly how much material is removed. The final fittings, including the handle attachment and other small components, are carefully installed and finished by hand. The completed kettle receives one last polish before the lid is fitted into place. What began as packed sand and molten bronze has become a functional vessel through molding, casting, heat treatment, precision turning, and hours of skilled finishing. And in a workshop like this, the most important machine is still the craftsman's experience. From giant bearings and tunnel-boring cutters to hand-finished saws and traditional bronzeware, every process shows a different side of manufacturing: precision, strength, craftsmanship, and experience. Whether shaped by massive machines or skilled hands, quality always comes from work. If you enjoy seeing how things are made, subscribe to Mr. Mechora, share your favorite process in the comments, and join us for the next factory journey.